So in this video, I will show you guys another example for superposition theorem. So let's dive in. So this is an example from Sadiku. This is exactly example 4.4. And here we have a huge circuit. But we don't have to worry about the whole thing. So first of all, we have to target the independent sources, right? So let's identify the independent sources. So here we have a 4 ampere current source. We have a 20 volt voltage source. We have a dependent source here, all right? So we don't care about that, okay? Just leave it as it is, okay? So let's not worry about that right now. So now what we have to do, so step one, we keep one independent source alive and kill the others, right? So what I can do is let's start with the 4 ampere first. Okay, so this is what we are doing for the 4 ampere. We will keep the 4 ampere alive and kill all the others. So we have only one, just 20 volts, so we will kill that. But first let me copy that. Oops. Okay, copied. Okay, I don't have much space there. Okay, so step one, I have to keep the voltage source, this one, alive. I want to keep this alive and I want to kill this one, okay? So how do we kill a source? Well, we turn it to 0 volt, okay? So now it's killed. And just do it here, I will just do it here. So 0 volt voltage source is just equivalent to 1 short circuit connection. So just it's short circuited now. Okay, and okay, so our job is to find out the current going through this 5 ampere current source, and this is actually I naught. So I forgot to mention that this here it says the 5 times I naught is the voltage here. So if here we have a current going through 2 ampere current, maybe if there's a 2 ampere current, then we have 10 volts here. If instead we have here 3 amperes of current, then it would have 15 volts. So this is a dependent system, okay? But the problem is we don't know what this current is until we solve the whole circuit. So that's why they are kind of a little different, okay? But not that much. Okay, now what we do? So this is our I naught, and our target is to finding out this I naught, okay? So I will write. Well, this is our question actually. So they're trying to find out what I naught is. So let me write it like this. So 4 ampere component of the I naught, and then the 20 volt component from the voltage source, right? And if we add their contributions together, we get the total current. But writing it like this kind of is problematic. So just let's write it like this: 1 prime and double prime. Okay, single prime and double prime. So here we have killed the 20 volt voltage source, right? The 20 volt voltage source was right here. We have killed it. So now we won't get I naught here. We will get just the I naught 4 ampere component of the just one component of the I naught current. Okay, so we wanted to write it like this, short form. So the current here will go going through this 5 ohm resistor will be I naught prime, and so this thing will also be just I naught prime, right? Because the current is I naught prime here. Okay, so everything is here is just single prime. So we have killed the other sources and kept one alive. We have kept the 4 ampere one alive. Now we have to do step 2. So step 2 was just to solve the whole circuit, right? We have to solve the whole circuit. So maybe we take this as our ground, then we have the whole thing as our ground node. We have this node here, then we have this one here, we have this one here, and this one here. Okay, so we have actually, maybe we call it V1, we call this V2, you call this V3, and you call it V4. And now we write the node equations for them. So we have, first of all, we have a voltage source here. So remember, we write the equations for the voltage sources first. So V3 minus V4 equals 5 I naught prime. And I should also mention that the I naught prime, we can actually just write it like this. I naught prime is just from Ohm's law. What is actually I naught prime? The current going through this 5 ohm, right? So we can write just V2 minus V0, that is just 0, divided by 5. Okay, so nicely the 5s cancel out. This is from the 5 ohm. And this is from just the 5 coefficient here. So we have V2 minus 0, so just V2. So we have one equation already, V3 minus V4 minus V2 equals 0. That's equation 1. Then we can write the KCL equations for this V1. So we can write KCL equation for V1. So we have minus 4, then we have 3 and 2 ohm resistors connected to that. So we write V1 times, we have 2 resistors. So this is, I'm writing for this one for node 1. Node 1 is 2 and 3 ohm we have here. So 1/3 plus 1 by 2. 1/3 here is minus V2 by 3, and the 2 ohm goes to node 4, so minus V4 by 2, V4 by 2, okay. And we have the 4 ampere current source, current going in, so we have minus 4 equals 0. And then we have V2, so for node 2 we can write V2 times what are the resistances connected to it, 1 ohm, 3 ohm, and 5 ohm, right? So let's 1 by 1 plus 1 by 3 plus 1 by 5, 1 by 5 minus the 1 ohm resistor is going to V3, so V3 by 1 minus the 3 ohm resistor is going to V1, so V1 by 3 minus 0 by 5, 0 by 5, because the 5 ohm is going to the ground node and equals to 0. So this is our equation. So this is just 0. So let's just write it like this. So this is our second equation, and this is our third equation. So we have 3 equations, and we have 4 nodes here. So we should get 4 equations. So where is the fourth equation? Right? So we just had 3 equations. So if you remember, if we have a floating voltage source, so here we have a voltage source. Yes, it is a dependent source, but still it is a floating voltage source. If such a thing occurs, then you have just have to use a super node, if you remember. So this is kind of a one giant node, you can think of it, or something like that, as you wish. Okay, so what we do is here V3 is connected to via 1 ohm, and V4 is connected to 2 ohm, like this. So if you remember here, for the super node 3 and 4, right? Node 3 and 4, super node 3, 4. So here the VIP will be the VIP will be both V3 and V4. So if you remember, whichever nodes equation you are writing, that's the VIP, and everything else has a minus coefficient in front of them, right? And for supernodes, we have both V3 and V4 as our VIP, right? So we will have to write like V3 times node 3 has only one resistance, so 1 by 1 minus that resistance goes to V2. So we have V2 by 1. Then this is the part from node 3, and then we have to write the part from V4. Okay, so what does V4 have? V4 have two resistors connected to it, 1 by 2 and 1 by 4. 1 by 2 plus 1 by 4, and this 2 ohm resistor is connected to V1, so we have minus V1 by 2, and the 4 ohm resistor is connected to ground, so you have minus 0 by 4 equals to 0. So this is from the node 4 part. Okay, so this is 0, so I'm just gonna write it equals to 0. So this is our fourth equation. This is our fourth equation, right? So if you solve the 4 equations, you will get some value. Okay, so the thing is, I have actually showed you the whole method. So I'm doing here a nodal analysis, and this is a kind of a complex nodal analysis, but this whole thing is just step 2, right? So you solve the whole circuit and you get the node voltages, and to figure out the current, you have to figure out the value of V2. And maybe after the calculation, you'll find out that the value of V2 is 15.3 volts or something like that. Okay, and then if you have V2, if you know the value of V2, then you immediately know the value of I naught prime, because this value will be just V2 divided by 5, right? V2 minus 0 divided by 5, just using the plain old Ohm's law. And so I naught prime will be V2 minus 0 by 5, which is just 3.06, something like that. Okay, so this is our sorry, not volt, sorry, this will be ampere. So this is our just one part of the equation, right? We just figured out the component from 4 ampere. Okay, so we just figured out the component from 4 ampere, and now we have to do the exact same thing. So we have completed a step 2. Now we have to complete the step 3, the same exact thing. So we have to solve the node analysis again. We have to do the same thing again. So this is a little cumbersome. This is true. Superposition theorem is a little cumbersome because you are doing splitting a circuit into 2, and kind of you can do this, you can directly do nodal analysis on the original equation, right? So but still, this is a technique you have to learn, so I'm just showing you, and in some cases this is helpful. Okay, so let's see how we'll do this. So step 3 is just repeat the whole thing. Step 3 was just repeat the whole thing. So this time we keep the 20 volt voltage source as it is and kill other independent sources. And remember, we don't touch the dependent source. Okay, so how do we kill a current source? Well, we set it to 0 amperes, right? And if you remember, current source, 0 ampere current source is equivalent to just keeping the line open, right? No connection here. So this is equivalent to an open circuit connection. And the thing is, the circuit kind of reduces, because if you have an open circuit here, so the current will never go through this path, right? There is no way to go here, so there is no road here. So basically you can basically what you can do is remove the whole thing, right? You can just remove the whole thing, because this is kind of just hanging there. No current will be here, so this is kind of useless for us to analyze this, because so there will be no current there. Okay, so that's one part of the scenario. And again, you have a different current here. So you have just the current from 20-volt voltage source. So we named it double prime, and here we'll have double prime as well. And then you have to solve the whole thing again. So maybe you use this as ground. We have this node. Okay, maybe use another color. We have this node here, you have this node here, then this node here, node here, node here. So a lot of nodes. Okay, so you can use maybe source transformation here. So the benefit of learning different techniques here, so you can use source transformation here and reduce the problem. Okay, and actually you could have done the exact same thing. I don't know. Is it possible? Okay, no, we don't have any resistor in series with the current source, so we have to we have to do node analysis there. But here we can do source transformation here and maybe reduce the problem. So whatever, you have to do this again, and yes, this is a little painful, but once you are done, you will get some value like this. Okay, I forgot to write the note here. Oh, and I should mention that maybe using a different name might be suitable for you, or you might confuse them with the earlier V1, V2, V3, etc. So this is a different circuit, but so you can name them differently, and they have no correlation to the previous equation because the circuit is different, right? So this is a new problem, kind of. New nodal analysis problem or something like that. And here you will find that I double prime is just V2 minus V1 divided by 5. And after all the calculations, you'll find out that V2 is 2.35 minus V1 is here 20 volts divided by 5, and you will get you will get a value of minus 3.53, okay, amperes. So you get a negative current. Now this is actually, you can see that since you have a huge 20 volt current, so the current will try to force this way. So of course the current is negative, right? Our direction is in the opposite direction. So whatever, now we have completed step 3 as well, and then we have step 4 to add them all up again. So we have the total current I naught will be I naught prime plus I naught double prime. So we are adding up the two components. So we have seen that I naught prime is 3.06 amperes. 3.06 amperes, and then we have 3.53 amperes from here, negative 3.53 amperes, and if you do the calculations you get negative 0.4706 current, something like that, 0.467. I guess this is good enough. So this is actually our answer. So this is how you do a complete superposition theorem problem. This is how solve it, and yes, it is a little cumbersome. Now there are two things to keep in mind. Why does superposition theorem works? Well, the thing is, if I write it simply, just using something like this, that if just something like the currents is the equations you have here are all linears, right? All linear things. So if you add up, maybe your equation is like V3 by 5 or something like that. So basically what I want to say is you can actually superpose voltages and currents, okay? So maybe if I told you to calculate the voltages here, so maybe you didn't have to find out the I naught current here, okay? So maybe I was telling you to figure out this voltage here. So I was what's this what this voltage is. So again, let's call that I don't know, maybe let's call it V output, VO, and again the two voltages would have been V output prime plus V output double prime from the two different components. Okay, this is what it's like, right? So the current, you can write it like this, so you can add up the component currents and yeah, all of them. But you cannot do this for power. Okay, so maybe I told you to figure out the power of this circuit. Okay, the power of this circuit. So you cannot add up the power components. Okay, so let's say P prime and P double prime. You cannot do that. Why can't you do that? Okay, so this is because something called linearity. So this is something I wanted to talk about. Look, all our equations are linear, right? We have nowhere square or something like that. Okay, everything is linear. We have nothing. Every equation here is linear, and we are adding up. And if you add up two linear equations, you still get the linear equation. So the problem with power is kind of like this, right? V squared by R. And so the problem arises that A plus B whole squared is not equals to A squared plus B squared, right? So if you just add up the power from two parts, you will get just A squared and B squared. You will not get the 2AB, right? So this is not actually equal to the whole thing. So this is important to mention, that this only works for voltage and current. You cannot superpose power because of that, because power is a squared proportional to squared of voltage and currents. Okay, so if you just add up the powers, so P prime maybe is like something like A squared, and P double prime is like B squared, but P is actually the effect of both of them, right? So A plus B whole squared. So on the right hand side you have A squared plus B squared, and on the left hand side you have A plus B whole squared, which are not equal, right? That's where the problem arises. So we cannot do superposition theorem for power. So keep that in mind. But you can do it for voltage and currents because they are all linear. Okay, so that's all about superposition theorem.